Hello dear students, welcome to mathematics class. In this class, let us discuss remaining two theorems, that is Cauchy's integral formula for derivatives and generalized Cauchy's integral formula. So the first one is Cauchy's integral formula for derivatives. So here this is the statement of this one, Cauchy's integral formula for derivatives. So here if f of z is analytic function within and on the boundary C, so means within the simple closed curve. So here within the boundary C of simply connected region D, and let A be any point within C. So here it is given that f of z is analytic within and on the boundary of that C, and A is the any point within the C. Then f dash of A is equal to 1 divided by 2 pi I integration over C f of z divided by z minus a whole square dz. So in the previous, that Cauchy's integral formula, that is what, f of a is equal to 1 divided by 2 pi I integration over C f of z by z minus a dz. So here power of f was 0, means there is no differentiation of the function f of a, but here we have differentiated f of a once, the power of z minus a becomes 2. So it is the Cauchy's integral formula for derivatives. So here to prove this one, we are going to use the previous theorem only, that is Cauchy's integral formula. So now let us prove this one. So given f of z is analytic, f of z is analytic within and on the boundary of C of the domain D. So by using this condition we can use the previous theorem. So here we know that f of a is equal to 1 divided by 2 pi I integration over C f of z divided by z minus a into dz. And let us consider one more function f of a plus h, 1 divided by 2 pi I integration over C f of z divided by z minus of a plus h dz. So instead of a, here we have considered a plus h. So therefore that z minus a becomes z minus of a plus h. Now consider this as equation number 1 and 2. Now subtracting equations 1 and 2. Subtracting equations 1 and 2. So we get f of a plus h minus f of a is equal to. So here f of a plus h minus f of a is equal to 1 by 2 pi I integration over C. F of a plus h is this one, f of z divided by z minus of f plus a plus h dz minus 1 divided by 2 pi I integration over C f of z divided by z minus a dz. Now let us take the common things in these two functions. So here 1 by 2 pi I is common, and integration over C dz f of z. So all are common, only 1 by z minus of a plus a and 1 by z minus a. So they are the different things. So therefore here 1 divided by 2 pi I integration over C and here 1 divided by z minus of a plus h minus 1 divided by z minus a into dz, sorry, f of z dz. So here we have taken f of z dz common and 1 by 2 pi I common, and both the integrals are having the same curve c, so therefore integration over c is also common. Then this is equal to 1 divided by 2 pi I integration over c. So here we will simplify this one. So here LCM is what? Z minus of a plus h into z minus a. Then this becomes z minus a minus of this one. Then this becomes z plus a plus h whole divided by z minus a into z minus of a plus h into f of z dz. So here in numerator plus z minus a plus a get cancelled, then it is equal to 1 divided by 2 pi I integration over c h divided by z minus a into z minus of a plus h into f of z dz. Then this can be written as, so on LHS we have f of a plus h minus f of a. So here this h can be shifted to LHS, that becomes 1 by h. Then here f of a plus h minus f of a divided by h is equal to 1 divided by 2 pi I integration over c f of z divided by z minus a into z minus of a plus h dz. So here this is the simplified result. Next, applying the limit as h tends to 0. So now applying limit as h tends to 0, then this becomes limit as h tends to 0 f of a plus h minus f of a divided by h is equal to 1 by 2 pi I limit as h tends to 0 integration over c f of z divided by z minus a into z minus of a plus h dz. So here let us apply the limit on RHS. So here after applying the limit, this becomes 1 divided by 2 pi I integration over c d f of z divided by, so here h tends to 0, so let us apply that limit, that becomes z minus a into z minus a into dz. And on RHS, sorry, LHS, that is limit as h tends to 0 f of a plus h minus f of a divided by h. So it is nothing but derivative of the function f of a. So therefore that becomes f dash of a. So now f dash of a is equal to 1 divided by 2 pi I integration over c f of z divided by z minus a into z minus a, that is z minus a whole square dz. So which is the required result, and this is called as Cauchy's integral formula for derivatives, because here in the previous theorem, that is Cauchy's integral formula, not for derivatives, because there we have f of a, but here it is f dash of a. So hence this is called as Cauchy's integral formula for derivatives. And the next one is a generalized Cauchy's integral formula. So previous one is Cauchy's integral formula, here generalized Cauchy's integral formula means it is for nth derivative. So here also same, f of z is analytic on a simple closed curve C and A is any point within C, then f power n of A means nth derivative of the function at A is equal to n factorial divided by 2 pi I integration over C f of z divided by z minus a whole power n plus 1 dz. So here this is the Cauchy's integral formula for derivatives only, but it is for nth derivative, hence it is called as generalized Cauchy's integral formula. So proof. So by Cauchy's integral formula, f of A is equal to 1 divided by 2 pi I integration over C f of z divided by z minus a into dz. Consider this as equation 1. Now we know that Lebanese rule for differentiation under integral sign, that we have studied in the 5th semester, that Lebanese rule for differentiation under integral sign. So here d by dx of integration over a to b f of x comma t into dt. So here observe this carefully. So here variable of integration is t and the function is of two variables x and t. So then we can differentiate this function with respect to the variable which is not the variable of integration, means we cannot differentiate this with respect to t because already the function is integrated with respect to t. So therefore we need to differentiate with respect to the remaining variable, so that is x. Then that is equal to integration over a to b dou by dou x of f of x comma t into t. So here this becomes dou by dou x because here the function is of two variables. Then whenever the function is of two or three variables, then we need to differentiate partially with respect to some variable. So here we are differentiating with respect to x, hence we need to consider the partial derivative of the function with respect to that variable x. So apply the same condition for equation 1. Now applying the Lebanese rule for equation 1, then f of a becomes f dash of a because we are differentiating that one is equal to 1 divided by 2 pi I integration over c f of z into, so here on RHS of the function we have two variables z and a, that a is nothing but a parameter, but here we need to differentiate with respect to a only because already the function is integrated with respect to z and remaining is a only. So therefore we need to differentiate partially with respect to a. So therefore f of z into dou by dou a of 1 divided by z minus a into dz by using this condition. So here d by dx becomes dou by dou x. So therefore dou by dou a of the function which is consisting that a. Then this is equal to 1 divided by 2 pi I integration over c f of z. This is minus 1 divided by z minus a whole square into minus 1 dz, because it is of the form 1 by x, that is minus 1 by x square, and the differentiation of that z minus a becomes minus 1, because derivative of a with respect to z is, sorry, with respect to a is 0 and its derivative is minus 1. So therefore it is 1 divided by 2 pi I integration over c f of z into minus becomes plus 1 divided by z minus a whole square dz. So here this 1 can be written as 1 factorial, because its value is 1 only, and divided by 2 pi I integration over c f of z divided by z minus a whole square dz. So it is f dash of a, because in the previous one Cauchy's integral formula for derivatives we got the same answer, 1 factorial divided by 1 2 pi I integration over c f of z divided by z minus a whole square dz. And here we need the nth order differentiation, so therefore here we have considered f dash of a. Now let us consider the second order derivative. So differentiate again with respect to a. So let us differentiate the f dash of a with respect to a, then f dash of a becomes f double dash of a is equal to 1 factorial divided by 2 pi I into integration over c f of z dou by dou a of 1 divided by z minus a whole square dz. Then it is equal to 1 factorial divided by 2 pi I integration over c f of z. So here its derivative is minus 2 divided by z minus a whole cube into minus 1 dz. Then it is equal to 1 factorial divided by 2 pi I integration over c f of z into, here minus into minus becomes plus, 2 divided by z minus a whole cube dz. Then this is equal to 2 into 1 factorial divided by 2 pi I integration over c f of z divided by z minus a whole cube dz, right? So here 2 into 1 factorial means that is 2 factorial, because 2 into 1 can be written as 2 factorial divided by 2 pi I integration over c f of z divided by z minus a whole cube dz, f double dash of a. So here in case of f dash of a, this is 1 factorial and this is z minus a whole square, and for the second order derivative that becomes 2 factorial and this becomes 3, and for third order derivative the same will be 3 factorial divided by 2 pi I integration over c f of z divided by z minus a whole power 4, and for fourth order derivative this becomes 4 factorial and this becomes z minus a whole power 5, and remaining things will be same. So therefore after differentiating, n times we get, so here let us differentiate n times, then we will get f power n of a is equal to, so here whenever the order of f is 2 this becomes 2 factorial, so here order of f is n, then that becomes n factorial divided by 2 pi I integration over c f of z divided by z minus a. So here the power of z minus a will be n plus 1, because in case of the second order it is 2 plus 1, so therefore here n plus 1 dz. So now this is the generalized Cauchy's integral formula for derivatives. So now let us consider some important points, that is, note here, if z equal to a means the point a lies inside C, then integration over C f of z divided by z minus a dz equal to 2 pi I f of a by using Cauchy's integral formula. If the point lies inside the given curve, then we can define the value of the integral as 2 pi I into f of a. So if z equal to a lies outside C, then integration over C f of z divided by z minus a dz is equal to 0. So means here, whenever the point A lies within the given curve, then we can define its value as 2 pi I into f of a. If the point A lies outside the C, then the value of the integral is 0, because we don't have the point A within C, then we cannot evaluate the value of that function at that point A. So these 2 points are important. Within the circle, then only consider the value of that integral, otherwise its value is equal to 0. So these 2 are important points.